Thanks for having me here. I'll get right in to this. This talk is essentially about information aggregation and building explanations in the context of science exams. If I'm a little tired today, it's because we just had a baby at home. This is Esri. She's only 7 weeks old today. She gave me 3 hours of sleep before I came here. But Peter Clark gave me my very first full night of sleep last night, so I am very thankful for him to do that. Okay, so what's in an explanation? Towards explanation-centered inference for science exams, or the subtitle for those who are fans of Dr. Strangelove, or How I Learned to Stop Worrying and Love the Table Store. So my long-term interest, as is many of yours, is in building inference algorithms capable of answering questions and producing compelling human-readable explanations by combining or aggregating information from multiple sources or knowledge bases. And so today I'd like to talk about 3 big questions that are empirically studied in the context of science exams. The first one is, what are the knowledge and inference requirements to automatically answer and produce explanations for the science exams? This comes from a paper that we had at Coling. The second is, many of you know, aggregating information and building explanations is currently very hard. And a lot of this is due to the lack of explicit training data for these tasks. And so the second task here is talking about how do we actually go about building a large database of training data for doing explanation building and information aggregation. And then finally, sort of a very big question here. If we examine very large corpora of explanations, are we able to find common, repeated explanatory patterns that can sort of help us perform inference and build explanations with very large numbers of facts? I will say that these last 2 questions are probably the most interesting to a lot of the folks here because you've been thinking about this a lot. But we'll briefly go and try and speed through a little bit of the first stuff. A little bit of motivation, because it's important to remember why we do this. So why build explanations? Why make our lives harder? There are a few reasons. Here are 3. The first one that many of you are probably familiar with as well is applications, right? For a lot of reasons, you probably just want to have explanations in automated systems, particularly for high impact domains where the cost of making errors is very high. Medicine is an easy one to pick off here. If you had an automated system or a doctor tell you that you needed surgery but not tell you why, you're probably not going to believe them and not have a lot of trust in that decision. My background is a mix of cognition and computer science, and I've been moving through a lot of the cognitive literature. And one of the more interesting things to come out of the cognition and pedagogy literature recently is that explanations when we're being tutored, when students are being tutored, and self-explanations when we're engaged in sort of self-directed learning appear to have a really important role in the learning process in terms of generalization. Generalization is, of course, something that machine learning models don't do very well. So I have a feeling that explanations might be a pretty big part of this. And then the last sort of bit of motivation is arguably generating compelling human-like explanations might help us constrain the kinds of knowledge that we're working with, constrain the kinds of inference mechanisms that we build so that the things that we create are going to be arguably more human-like than they might otherwise. That's wild conjecture, though. So to take a step back and ground this task, here's an example science question from the New York Regents Science exam. Which of the following is an example of an organism taking in nutrients? The answer is, of course, B, a girl eating an apple. And note here how the negative examples are really well designed. They're very good distractors. Each one contains an organism, like a boy or an insect or a dog. Many include things that are high associates of foods, like tomatoes or leaves. And so very rarely for these complex inference questions are we lucky enough that in some corpus we're going to find a passage that directly answers this. Even if your corpus is the size of the web, it's really unlikely that it's going to happen in general. More likely, what we need to do to solve this question while producing a human-readable explanation is to aggregate a variety of different pieces of knowledge from a variety of different sources. And so we need to know that a girl means a human girl, that humans are living organisms. Maybe we find this information in simple Wikipedia. We also need to know that eating is when an organism takes in nutrients in the form of food. We might find this from the study guide, the Barron's study guide. We also need to know that an apple is a kind of fruit and that fruits are kinds of foods. And so these sentences, these 5 sentences, if we sort of aggregate them together conceivably for this sort of toy question, we can form a compelling human readable justification. And of course, what many of you have probably already picked up is that we can frame this as a problem of building a graph of sentences that together form that explanation that help answer the question. Here you'll notice that most of the explanations that I build have edges where, that are based on basically lexical overlap with the question or other explanation sentences. And most of the graphs that we'll look at today have this sort of lexical overlap as the connecting glue. So bringing this into the real world for a second, and one of the things that's remarkable is that we can actually do this. I find this absolutely wild. We can actually build explanations, at least in part. We can assemble graphs that make seemingly reasonable explanations for some subset of elementary science questions. There's, of course, beginning to be a number of QA systems that aggregate information. Table ILP here at AI2 is a very cool one. I think that we also have a couple of systems, including with Hyung here, that aggregate OpenIE triples. I'm showing this example here only very briefly as sort of motivation. But one example system that we developed at Arizona is called text aggregation graphs. And it helps build explanations by decomposing free text sentences read in from study guides or simple Wikipedia based on certain clausal and prepositional boundaries, and it connects them together. So there's 2 connected things that I briefly want to mention here. One, because there's no explicit training data available for building explanations or aggregating information together, we had to model how to build explanations as a latent machine learning problem. So what we largely do here is connect knowledge based on whether that knowledge makes a particularly well-connected graph. There actually aren't a lot of cool or interesting, from a scientific standpoint, connectivity or semantic features. So it doesn't really get a lot of the common sense reasoning or world knowledge that you'd really want to do, which sort of motivates a lot of the current work in the corpus that I'm going to discuss in a bit. But it is neat. This is an actual example. So which of the following organisms is a producer? Of course, it's grass. The explanation that the system gives you is a producer is an organism that produces its own food and is food for other organisms, usually a green plant. And grass is a green leafy plant that covers the ground. And we see that these sort of connect on the idea that a green plant is a producer and grass is a green plant. 2-hop inference. So there's a couple things I want to point out of this, just sort of to motivate our current work. The first is explanation quality. We found that when we manually rated the explanations that this system built, that they were about 60% of them were good explanations, that if you gave them to a human, they would sort of think that they were good, compared to a TF-IDF model, which gave only about 45%. We rated these on a 4-point scale, and we found that the main reasons why we were building more good explanations was because we were putting 2 separate facts together that the IR model basically wasn't able to combine. The other thing that's the more telling graph, and the main reason why I show this, those of you who have worked with information aggregation systems will immediately recognize this. The basic idea is you begin to aggregate information up to some certain number of sentences that you aggregate, the performance goes up, and then it immediately just starts to go down. Aggregating, we call this phenomenon semantic drift, which is the tendency when you're aggregating to make missteps in making long chains of information. So for example, one sentence might include that a flower is part of a plant, and then the next might include that a plant is a factory, and so you can make missteps very, very quickly.
Is that more of a problem with retrieval rather than the fact that you're aggregating over more than 2 sentences?
I think it's a problem with being able to determine the context of the things that you're picking out to try and aggregate. It's a good question, and I think I'm going to speak to it right here. thank you for the segue. You might ask, as we just have, how big of a problem is this? Where's the problem coming from? How hard is information aggregation? Imagine if you were to traverse a knowledge graph made out of sentences where the sentences are connected based on lexical overlap, so shared words, with the goal of making explanations for question answering. What proportion of the traversals in the graph are going to be any good? What proportion of the traversals are going to lead you to sentences that are going to be useful for building explanations? I've wanted to know this for years, and so finally I took 3 days and I just did it. I grabbed 14 representative medium difficulty elementary science questions. I grabbed 3 corpora, Wikipedia sentences, study guides, and a corpus of explanations that I'm going to describe in a moment, and rated all of the cases where the sentences from these corpora had some shared words with these 14 questions. And I rated them on a 4-point scale for how useful they would be, how useful these sentences would be for building these explanations. What I ended up finding out is that a couple of things. First, is sort of obvious. The more shared words you have in common, the better the sentences are going to be for your task, which is you might expect. But the more important thing is how very low this estimate is. So if you're just grabbing Wikipedia sentences, only about 0.1% of them are useful for the task. And a lot of the time we use Wikipedia because it's open domain and it's very large. For study guides, only about 2% of them. And then in the ceiling performance here, so if you're just using a corpus of only explanations that are exactly designed to build explanations for these questions, it sort of peaks at around 5%. What this means is that if you want to build an explanation with only 5 facts in it, then your chance performance for being able to do this, in the worst case, is 1 in 100 trillion, which is terrible. And in your very best case is 1 in 5,000. So it's a hard problem. And so we need to understand a bit more about this problem, which is, of course, probably not news to many of you here. Best AI still flunks 8th grade science. So information aggregation is hard, but let's empirically study a little bit more why it's hard. This study I'm going to go through a little bit quickly, but it provides a lot of motivation. So question number 1, how many facts are required to build explanations? 2, what kind of knowledge is actually needed in these explanations? What pieces do we have to use to build our puzzle? And then sort of a quick aside at the bottom, are models that claim to be doing inference actually solving more inference questions, or are they just answering more simple questions? So there's a couple different ways that you can do this analysis. One is top-down, and one is bottom-up. The top-down study was done already in this really cool paper by Peter Clark at AKBC 2013. And they basically did an analysis where they divided questions into 7 different knowledge types, 3 of which I call retrieval methods, so questions that are primarily testing taxonomic knowledge, which is about 2%, definitions or properties of objects, and then complex inference questions like examples of situations, the causality and processes that a lot of us are interested in, and then the domain-specific models that really capture sort of common sense reasoning, information aggregation, world knowledge, causal inference, and maybe even cognition. One of the difficulties with doing it top-down is that while a lot of the questions from the New York Regent Science exam, for example, are very pure examples of this, a lot of the time questions don't easily fit into a specific category. So for just grabbing this question, many bacteria are decomposer organisms. Which of the following statements best describes how these bacteria help make soil more fertile? The answer is, of course, D. The bacteria break down plant and animal matter. So the question is, which of the 7 knowledge types that we've identified is this question? And so you might originally think that it might be a causal question, of course, because how do bacteria cause soil to become more fertile? But decomposers are a stage in the life cycle process, and this is probably the curriculum topic that it would be under. And of course, decomposers are part of an ecosystem model of recycling nutrients. And so you get where I'm going with this. You can basically do this with most of the 7 knowledge types. So if we go back to sort of our toy example about building explanations, One of the things that we clearly notice when we're looking at explanation sentences is that we require many different kinds of knowledge to answer very specific questions. Taxonomic knowledge, definitions, actions, and so on, even in this simple example. So maybe a more productive way is to look at this bottom up. We'll build gold explanations, and we'll look at the knowledge and inference requirements that way. So bottom up. What we did here, our annotation method for building sort of this explanation-centered analysis, we generated 400 explanations for questions in the training set from the open corpus that were, the explanations were designed to have as much as possible the knowledge and required to arrive at the correct answer. The sentences were drawn from grade-appropriate resources where possible, and if we couldn't find a sentence in the corpus that was something that we felt we needed, we constructed one using the same sort of simple language, grade-appropriate language that we get. A few additional criteria, and these are going to be important in the later work, that we added together. First, each sentence should be on a single topic so that we can facilitate automated analysis. Second, we should reuse identical sentences, again, to facilitate automated analysis. So if you need to know that Arctic rabbits have white-colored fur, say it in the exact same way. Don't use different versions of it. And third, the sentences need to be explicitly lexically linked to each other. So if you have a sentence that mentions melting and a sentence that mentions heated, you're going to want to have a sentence that bridges those together, that melting happens when solids are heated, for example. I sometimes call these bridge sentences, but in later work, I might say they're lexical glue. They might not have a lot of content, but they help build the graph. So on average, the gold explanations that we generated for each question had about 4 separate facts in them. So 4 facts required to explain each question. Here are a few examples. What form of energy causes an ice cube to melt? The answer is D, heat. The explanation that we generated is an ice cube is a solid. Changing from a solid to a liquid is called melting. Melting happens when solids are heated. Heated means adding heat. This is a particularly lexical gluey sentence. And then heat is a kind of energy. So then to better characterize the knowledge and inference requirements of these explanations, sort of used a data-driven approach and really looked at all of the different explanation sentences and identified about 20 different common semantic relations that happen to be in them. I divide them into 3 separate types: retrieval relations, inference supporting relations, and complex inference relations. Here's a bunch of them. Just to orient you to this table, the first column is the relation type. The second column is the proportion of explanations that have at least one relation with that type. And then the third is just an example. So, for example, taxonomic relations occur in 83% of questions, so they're all over the place. And an example might be a plant is a kind of living thing. There's a couple of things that immediately stand out. First is that with this finer grain analysis, we see types from the first analysis, taxonomic definition, properties, whatnot. But we also see a lot of new ones, made of, example of, contains, and whatnot. The other thing is that the bottom-up analysis gives us very different estimates of the kinds of knowledge that are required. So with the original top-down estimate, taxonomic knowledge was central to only about 2% of questions, but here we're seeing that almost every question really requires this. They're sort of similar stories all the way down. For time, I'm going to skip over the second category, the inference supporting, and I'll just quickly mention here the complex inference types. One thing to mention is that these are n-ary relations, they're not triples. So for example, the changes relation, which occurs in almost half of the questions, talks about who changes what from X into Y. For example, boiling changes water, or boiling changes something from a solid to a liquid, rather. So a couple other common relations I'll just quickly mention. So causes, transfer relations, so who moves something from where to where, a source to a destination, if then, and of course coupled relationships, so as X increases, Y decreases. So a quick empirical evaluation. Are models that claim to be inference models actually solving more inference questions? Or are they just answering more of the simple questions correctly? What we ended up doing here, and I'm just going to buzz through this quickly for a moment. This table lists This table lists the performance of an IR model, learning to rank model, and the table ILP system. The IR model used both a study guide corpus and the table store corpus, and the table ILP, arguably an inference system, used the table store corpus. And what we see is that the IR model really doesn't differ substantially when it's using the study guides versus when it's using the table store, whereas the table ILP system, which is able to combine knowledge, bumps up performance wildly. More than that, a lot of the performance gains, I'm just going to highlight the ones for the inference here, a lot of the performance gains are specifically in questions that we've labeled as requiring complex inference. They can be up to 20% over average performance.
Peter, sorry, quick question.
Of course.
So given that, I'm just curious why you say that table IOP arguably performs inference.
Inference is a loaded word. I'm hedging my bets. So what is inference, right?
What is explanation?
Exactly. That's what I'm trying to figure out. I think we had this conversation over dinner. Do you have a running definition for what an explanation is? It's a hard question. I do. I don't know if it's any good. I'm going to buzz through this again for time because I think the second and the third questions are the most important. One of the first observations, though, is that table ILP is basically is better at almost every relation. But there's, in particular, some relations that it does better versus not. So for a lot of retrieval relations, table ILP is actually doing very, very good. But there's specific lower than average or sort of deficits in particular relations. So for example, coupled relationships as x increases, y decreases. You get this a lot in the predator-prey population questions. If you have a lot of prey, what happens to the predators and so on and so forth, predator populations. And if-then relationships as well. So I'm going to segue a little bit and switch gears and talk about corpora of explanations and the properties of the knowledge graphs that result. This is just sort of to get us in a graphy state of mind. The first study told us a few things, that we need to aggregate an average of 4 to 6 facts to answer and explain most questions, and the 24 or so common kinds of knowledge that we have present in these explanations. But how do we actually learn to connect that knowledge? How do we actually learn to build explanations? We still have a need for a database that has explicit training data for this task. Now, as a postdoc, I sort of toiled away for years trying to do this with that text aggregation graph system latently. Now I'm a professor, I can get my students to toil away on building me a giant corpus of this, so that's fantastic. In the second part, we're going to look at building a corpus of very detailed explanations, and it has a couple of specific needs that we outlined. First, the explanations have to be very, very detailed, and we'll see what that means in the next slide. They have to be in some semi-structured computable form that's lexically connected, that allows us to build explanation graphs. And where the Coling data set, to be completely honest, generated hundreds of somewhat rough and ready explanations, we really need to figure out a way to create detailed, consistent, repeatable, and high-quality explanations for each question. Yes?
When you say 4 to 6 facts, do they include those lexical glues?
They do include the lexical glue. That's a fantastic question. The lexical glue inflates the estimate by about 2 in the world tree corpus. The Coling corpus gave us an estimate of about 4 facts on average, but the range is quite large, about 1 to 12. In the world tree corpus, which has about 1,700 questions, the average is 6 per question, and the range is anywhere between 1 and 16. Lexical glue tends to inflate it on average probably about 2. That's a great question. We've been working on this corpus for a while. I secretly tried to make it 3 times and I failed. I'm not going to tell you about the first 2, but we finally got it to work. I'll describe the process and some of the analyses that we're doing to understand more about the question of what's in an explanation. I call the corpus world tree for a reason that'll become apparent when you see the visualization in a second. Each of the explanations here is manually authored, and creates sort of a manual explanation graph. The critical bit, though, with the corpus is the level of detail. We try and target our explanations at the depth that they would be meaningful to a 5-year-old child. So we're really drilling down to have a lot of the explicit sort of common sense reasoning and world knowledge that you would get at that level. For example, with this question here, which characteristic would best help a tree survive the heat of a forest fire? The answer is thick bark. For a domain expert like a teacher, just having the explanation, bark is a protective covering around the tree, is probably enough for them, right? But if you don't have a lot of the explicit world knowledge that computers just don't have, right? You really need to be explicit about this, or at least that's my hypothesis. Things like fire causes harm to tree and other living things and so on. So I mentioned that the explanations are structured as lexically connected explanation graphs. I'm only going to draw this once or twice because it's messy, but this is what I mean. Each fact takes the form of a row in one of the semi-structured tables in a table store. We have 62 tables, which I think is about the same as the Aristo table store. Pretty much the same kinds of knowledge that you might find in some parts of the table store and others we've expanded a bit. Taxonomic parts of things that you're going to find, as well as process roles, changes, causality, coupled relationships, things of that nature. Our tables and our design of our tables came directly from that analysis I just showed you of those 20 types, which is why I think it's been so productive. Each row in our explanations are lexically connected to either other rows in the explanation or the question or answer. As you can see, the explanations have a lot of fine-grained structure. Something that I'm not showing here is, because I can't draw it, is that our tables have as many as 26 columns in them. So we've really tried to narrow down a lot of the knowledge and really strongly compartmentalize it so that we can use it as training data. So world tree corpus, you can see why. Visualization is sort of a hobby of mine. I have a lot of fun with it. In this graph here, each node represents a question and its explanation. And the edges represent when explanations for two questions share at least two common explanation sentences, or two common table rows, you can think of it. And as you can see, what that creates is a lot of structure in that questions that are talking about similar topics sort of naturally tend to cluster together. Things like inherited and learned characteristics. A lot of the astronomy questions are down here, sort of planetary motion is connected to stellar distances and whatnot. I'm just going to zoom in on a couple of areas of this graph here. I'll skip that one. This side is particularly interesting. At the top we have a cluster of camouflage questions, and it turns out that a lot of the camouflage questions have explanation sentences in common with the environmental adaptation questions, because camouflage tends to be an environmental adaptation. If you're a white rabbit, you have white fur because you're a snow hare and you live in the snow and need to hide from predators. But it's also connected with magnification questions, which is kind of interesting. It turns out that magnification is used to make things easier to see in a lot of the ways that we've expressed it, whereas camouflage makes things more difficult to see. So we get a lot of similar questions there. Erosion and weathering, you might expect that there would be separate clusters that would have some shared knowledge, as you expect. Different clusters for measuring time, measuring wind speed, since those tend to be their own. Sound energy and echoes, which again have a little bit of shared knowledge. This one's kind of interesting. I'm going to zoom in on it. Gravity and sound energy. Does anybody know why you would have those two clusters connected? Yeah. Gravitational waves in elementary science? I want to go to that elementary school. Here, this is cool. Okay, sound energy. Here's a question. The sound heard when a piano key is hit is caused by whatever. Gravity, we've all seen these questions. A marble is dropped in a glass of water. What force pulls it down to the bottom? Here's an interesting one. When a book is dropped onto a wooden desk, the molecules begin to vibrate. which of these is produced? So we have a question about a book dropping gravity, a question about what happens when gravity causes things to drop sound. Kind of cool. Anyway, you can explore this all day. There's an enormous PDF of this that you can download. And I was going to bring a poster of this and print it out so that you could put it on a wall. Then I realized that it would have to be 4 stories tall to be able to read the questions. So, okay. A few comments on, yes?
In the previous example, for the explanation, do you really need gravity? It's more about molecules causing things to vibrate.
So that's a great question. Do you need gravity in this explanation? I would have to think about that, but we've erred on the side of really describing everything that the question is asking for, sort of leaving no stone unturned so that you have ridiculously detailed explanations. Here I would argue that you need the knowledge that a force is interacting on an object to push it against another object, and that causes a sound. It just so happens here that you need to probably figure out that that force is gravity, because you don't get gravity, you get a book is dropped. And so dropping tends to cue gravity. It's a great question. Okay, I want to spend a moment talking about actually building this corpus, because it was a lot of fun and I failed a couple of times before I got it right, and was able to de-skill it to the point where some very clever undergraduates are able to be very productive at this. A huge part of successfully building this is the tools and the workflow, and if any of you want to talk about this in more detail later, I'm very, very happy to. We created a web-based tool that allows for easily searching the table store to build explanations for a given question. It visualizes the explanation graph as we're building it. This was a critical part. I didn't have this in the first version, that allows the annotators to quickly understand how connected the graph is, but also when there's words that aren't highlighted, it's a good indication that they need to express that knowledge. The table store itself, we store this in a Google Sheet, which is simple, but it allows simultaneous collaboration and authoring. When the author creates an explanation for a new question, they work on the explanation. They usually go from the central or big idea of the question, get that down, and then start grounding it in the specific example that the question has. An earlier version of they search traditionally for table rows that happen to be, that happen to express the knowledge. So this is a query-based search that brings up table rows, as well as entire complete explanations to help keep the consistency up. If a table row doesn't exist, they go over to the table store and they author it. One of the critical bits that we discovered is that it's very, very important that when you author a table row, you be able to import it immediately back into the tool. An earlier version of this, it took almost 45 seconds to import the table store. And that doesn't sound like a lot of time, right? But when you're building an explanation, it kind of interrupts your table or your train of thought. So we ended up rewriting the Node.js library for Google Sheets to get it down to a second. So it's very, very quick. Had a couple of specific goals here. Multiple people have to be able to work it on the same time. It can't interrupt their workflow. It has to be usable. You have to be able to author, review, and complete 5 explanations per hour. Depending on the way that you look at it, that sounds both like a very low number and a very high number. We have a very long quality assurance step. It might only take 2 minutes to generate most explanations unless they're pretty long. But it goes through a 4-step quality assurance process to make sure that we get it right. The other bit that I think is critical to this is that it's a hard task, and it's way harder than I had fully appreciated. And a lot of the time when you see a new question on a new topic, you're not quite sure how to express the knowledge. So the way that we do this is our tables are completely malleable, and they're designed to be refactored very frequently. Instead of storing explanations as lists of the content, we store them as references to a specific row so that we can go back and refactor it. Okay. So, yes?
Is there any possibility to sort of take like several explanations which aren't good and then use the inference procedure to try and extract out the good aspects of those explanations?
So that's an interesting question and something that I've been wondering about. The question is, if you have a partial, I'm going to reframe your question. If you have a partial explanation, can you use the gold explanations to repair that? And I think you can, and I think that that's actually a really productive way of framing the inference problem by grabbing a partial explanation and then repairing it. And that's actually what the last half is about that we're going to see in a second. It's a great lead-in. My favorite parts about this corpus and having a knowledge resource like this that I don't think we've really had is the kinds of automated analyses that you're able to then do on it. I'm going to show you, I think, two. This one here is the knowledge growth of the corpus. So one of the questions that a lot of us have had is how big is the idea of elementary science? What are the core concepts in it? How many do we need to do? Do we need 1 billion? Do we need 1 million? Do we need 100? This here is a Monte Carlo analysis that shows the number of unique table store rows required to answer a given number of questions. The corpus is only a little less than 2,000. The released one, we're up to almost 2,500 right now. The blue lines are measured values here. So on average, for 1,000 questions, you need about 2,700 rows. What's remarkable here is that when you try and fit this curve, it correlates 0.999 with a proportional decay relationship. This is, almost radioactive decay, but for explanations, which is wild. What that allows you to do is a couple of things. First, if you're a room full of people who want to build a lot of explanations, it allows you to estimate how long it's going to take. Second, it estimates the size of the domain with a whole bunch of asterisks on it. Here in particular, it says that the number of unique questions that we could generate with the natural variation in the questions is about 10,000 questions, and that it would take about 6,000 table store rows to generate this, which is wild, right? This is a very interesting result. Of course, if you had a given question, you could make variations of that question very easily, right? You could swap out a specific instance of a food with another instance of a food and generate 100 different versions of that question. But this is sort of a very interesting table here.
Peter, sorry
yes.
to slow you down.
No.
This is really fascinating question and a
Yeah.
fascinating result. I guess I'm struggling a little bit with a couple of things. One is just visual, and so you can just tell me that I'm wrong, right? But it looks visually, right, like there might be other curves that fit the data equally well. So you're really getting that decay signal in that early part of the curve that gives you that sharp asymptote in the later part of the
So that's a fantastic question. So am I lying to you? Is this curve?
I was trying to be a little bit more polite.
No, you should call me out. That's a great question. The curve, it really seems like these endpoints on the curve, if you render them properly, give you this relationship. I had originally thought that this curve was approximately every doubling of the number of questions halves the number of table store rows. It turns out that it's a little bit more complicated than that. I am reasonably confident in this curve. I'm not 99% confident in this curve. The correlation is 99% confident, but of course, it could be anything. I think that this is right. One of the interesting things that we're going to see right now is that we have data points up to here. So what does it look like when we render this? It takes a day or two to run this. So, yeah.
Got it. Yeah, that would be really interesting.
The difficulty, so one of the difficulty, but also the cool thing about it is that we only have 2,200 elementary science questions, and only about 80% of them are amenable to textual explanations like we're doing. The spatial questions are really hard to do. So this is kind of the number that we're going to get. We might, maybe we could find another couple hundred questions, but we're not going to find 10,000 elementary science questions. So this is as far as we go. With the with the 8th grade questions, my goal is to try and get 10,000 8th grade questions. And so that's really going to allow us to really render this curve properly, I hope. If we pour on 8th grade questions on here, we're going to mess with the curve a whole lot because we have suddenly 30 different topics that we're including in this. I think that the slope of I think that the decay factor of this curve depends not on the, well, I think it depends upon the number of individual topics that you have in the domain. I don't know that it depends upon the size of the domain. I secretly hypothesize that if you were to do this for 12th grade, 8th grade, even AP, that it's probably not going to look all that different, that it's probably limited by the proportion of things that you can teach a student in a year.
So the thing that I find surprising, and again, sounds like you're not actually, so you're qualifying the set of questions here in a number of ways. That wasn't explicit in the slide. So first one is, right, it's just 4th grade science, is that right?
Elementary
And
science.
secondly, you're not using all the questions, you're only using the ones that are, quote, amenable to explanation?
Yeah, the amenable to the style of explanation that we do here, the textual explanation. So a question about orbital rotation is a little bit difficult to write down. You really probably need a diagram for
So
that.
that also helps to explain
Yeah.
the small numbers. But then the last one is, often the questions, right, are applying a general concept to a specific situation that might involve squirrels, but it might involve voles, and it might involve moles. And as soon as you have that noun, right, that's where it seems like it could explode. And likewise, we have questions about New York, but they could have been about New Jersey. So
Exactly.
how do you just say, oh, but they didn't use New Jersey and they didn't use voles and therefore it's 10,000, or do you?
So, beautiful. So that's why I put two things. First, that's why I put my asterisk on here with the natural variation in the questions. So they don't tend to use voles and too many other animals. There's a dozen animals that they really like to use. So that's the natural variation in the question. The other way of doing this, and I'm not sure if I have the slide or not, but you can break it down by the specific table, the knowledge that's in the specific tables. We have maybe 60 rows in our changes tables or in our causality tables that are really core scientific concepts. And then you can instantiate those rows in properties tables that are 10,000 rows long, right? And so if you're looking at the core scientific knowledge, I think it's a bad question. I think saying what's the core scientific knowledge is not a great question. I think saying what's the core causal scientific knowledge for an elementary science question? What's the core knowledge that they need about transferring things or about specific knowledge types is a better way of framing the question.
So let me just make one observation, then stop derailing you. But
Yeah, no.
This is really fascinating. So my one observation is that if one were actually to build on this estimate, you would result in a system that's particularly brittle, because if the examiners decided to use voles, or vole is a particularly obscure animal, but if they went from squirrels and rabbits, which they usually use, to pigeons or something, the thing would fall apart.
Exactly.
And so I guess I would hesitate to build too much on this observation.
So the claim isn't that this is all you need to solve the questions. Again, that's why I stick in my asterisk here, the natural variation in the questions. The claim is that this is probably, to an order of magnitude, not a bad estimate for the core scientific knowledge. If you wanted to use this to solve a question, the very first thing or to solve stuff in the test set, the very first thing you're going to do is pour on the Aristo table store, which has a huge amount of, animals in it, for example, or geospatial locations, so that instead of New Jersey, you're doing it in Arizona. Yeah, you'd absolutely need to do that. The benefit of doing it bottom up versus top down is that top down you say, what kind of knowledge do we need? Maybe I need 1,000 animals, and you start spending your time making 1,000 animals. Here we say, what kind of knowledge do we need? We're going to make thousands of explanations and see it, and then we can examine those explanations and say, okay, we do need animals. We've only said that we need 12 animals to solve the explanations that we have, or to solve the questions that we have now. We know we need animals, though, so get Bob over there in the corner to go find all the animals and add those in, so that our table store goes from 6,000 rows to 20,000 or 30,000 with a natural variation, or with way more than the natural variation that you're going to see to make it robust to variations in the questions. Does that answer your question? Yes.
One thought on that, I think it seems valuable to perhaps tag all the rows as is it capturing an atomic something, or like a science principle or something at a higher level that captures more than one individual fact, and then draw the same curve differently for the two kinds of facts.
That's a great idea. We did it, and the corpus has for every explanation, we have tagged the role that the explanation sentence has in that. We identify, I don't talk about it here, it's in the paper. we have identified roles. Central concept, which is basically core scientific concept, or the main thing that the question is asking. Grounding, which is exactly the kinds of things that we're talking about here. It doesn't, a bird is a kind of animal or something like that, or a vole is a kind of mammal that instantiates it. We also explicitly call out lexical glue, so that if you wanted to just look at the core scientific concepts, that's what it looks like. If you just do the central concepts, I think it's about 30% of this estimate. So you would go from 6,000 to about 2,000 rows. Great questions. Okay. The other property of the corpus that I'm going to chat about, and I'm just going to run through this somewhat quickly, is one of the things that many of you are probably thinking when you're talking about having explicit training data is, assuming that I was able to come up with a method of repairing explanations or building explanations from scratch, and I compared the new question that I'm looking at, to some other number of questions, assuming that I could identify some level of overlap with those questions. What's the minimum level of overlap that I would need to be able to develop a new explanation? So imagine that I was just starting out and I came up with a new inference method that, assuming I had a question that had, 3 sentences of explanation overlap with a new question, I would be able to find it and rebuild it. Or say I was amazing and I developed a method where I could only, as long as I got one of the right explanation rows, I could repair it and build the rest of that explanation. This graph basically speaks to that and says, in the corpus, for a given question, how many other questions, what proportion of other questions have a certain level of overlap in terms of explanation rows? So this blue line here is, for a given question, what proportion of other questions in the corpus contain at least one explanation row in common with it? The caveat here that gets back to your question is, they have to have a central role in it. So these aren't, we're not tagging, bird is a kind of animal here. These are core scientific concepts, boiling is changing from a liquid to a gas and so on and so forth. So what we see here is, and this is of course Monte Carlo analysis, so it's done versus the number of questions so that you can estimate how many questions you would need to do this. What we see here is that the cluster size increases logarithmically, which is cool, but it also allows you to estimate what you need. So if you need 2 sentences of overlap in your explanations, you would need nominally only about 600 questions to be able to get a passing grade of 60% in a perfect world. Whereas if you need 3 sentences of overlap, so quite a bit of overlap, you would need about 4,000 questions. If you need a huge amount of overlap, if you need 4 or more, the slope on these is terrible and you would need a corpus that's just enormous. So if you are thinking about your question about the idea of repairing, then this gives limits on it. The very maximum that you're going to be able to do that method on is with about 4 or with about 3 sentences of overlap, unless you come up with a different method of doing it, a method of abstracting it. I'm going to skip over the table row frequency in the world tree corpus slide here. This data is in the paper, but you can break it down. Yes?
So, a question about that previous graph that you had.
This one here.
To what extent is the coverage of your corpus? Because you can imagine that this is increasing, but it's because there are some new questions which heavily overlap.
Right. So some questions heavily overlap. There's questions that are essentially repeated. There's not too many questions that are repeated sort of verbatim, but there are a lot of questions that the basic idea is repeated. It's just instantiated. It uses, a different kind of bird or something in it. In general, the hope is that this kind of brings all that out in the wash, that you have some questions where you see 3 different versions of them in the corpus, and some questions where you only see one version in the corpus. inherited characteristics are a really good example of this. There's 20 different inherited characteristic questions in the corpus that are all pretty similar to each other. Whereas there's, you know, 1 or 2 questions about the butterfly life cycle of metamorphosis that are very, very different. So the hope is that this comes out in the wash. Yep. Yes?
Does this analysis implicitly assume that if you and I wrote down explanations for a question, will come up exactly the same?
It does, and that is a questionable assumption. One of the studies that I would love to do, if I can convince 2 other undergraduates to spend their summer writing explanations, is to get them to remake explanations. And I actually want to do it in 2 different ways. One where they don't get the table store that we've made. They have to come up with a completely new table store to see what the variation is. And the other one is they get the table store, but they can add stuff to it if they want to. In a perfect world, I've been dreaming up how you could come up with a protocol to crowdsource this. I don't think you're going to be able to do it. I think I can de-skill it from the level of a postdoc to the level of a clever undergraduate. I don't think I yet know how to de-skill it to the level of a Turker. Yes?
Since you brought up crowdsourcing, I would like to talk about one particular line of work that somebody is doing. It has nothing to do with NLP or inference. So there is someone called Joseph J. Williams, who's an assistant professor now at NUS. So he is using MOOCs to actually crowdsource explanations. So on your MOOCs have this videos, lecture videos, and questions pop up at some point while you are watching the video. Okay, so you get the learners to, you have to provide explanations. Coursera provides some explanations for the answers if they're giving wrong answers, and some of the learners, if they feel that the explanation is not quite good enough, they can provide an alternate explanation.
Additional.
Explanation.
Yeah. So.
And then other learners can actually vote on which explanation is better.
Right.
So you can use some sort of a Bayesian prior and then build a probability tree to find out which explanation is better. And that sort of a crowdsourcing framework is proposed, and he has published quite a few papers.
That's interesting. I'd be interested in getting that information and the references. The one issue that I have potentially with crowdsourcing is that I don't know if you can do it without training to the level of a 5-year-old child to get that level of world knowledge. One of the issues that my annotators have is that it takes a lot of training to be able to get down to that depth. There's this interesting Reddit thread. Explain something to me like a 5-year-old child. And I went through there and I was like, this is a gold mine. You know, Christmas comes twice this year. I'm just going to mine this out and away we go. I don't need to pay these annotators. Turns out the explanations are terrible. I'm sorry if anybody here contributes to them. They're not like a 5-year-old at all. I don't know what a 5-year-old child looks like in their household. So it's just wild. I have a question. We are at 55. I have one more study that I'd like to tell you. Are human beings able to stay in this room a little bit longer? Leave if you have to. This is the cool stuff. You're not going to want to leave, Oren. This is the really cool stuff.
Well, I do have to go to
Okay.
later, but you'll have to tell me about our lecture.
Of course. Okay. So one of the other things that I will say is that I'm just going to quickly get on is.
So we do not stop at 12, just so.
Oh, okay.
Sorry, 11. So
11. Okay.
whatever you can get into the last.
Whatever we can get. Okay. So here's our quick whirlwind tour. So you might also say, okay, we have this giant corpus of explanations. Can we use it to do inference? Can we use it to rebuild explanations? I'm going to buzz through this. The basic idea here is to see whether you can take parts of explanations, parts of 2 or more explanations, merge them together, adapt them in some way, or add to them in some way, and rebuild gold explanations that you haven't seen before. This is from an AKBC paper. I won't go through this example with you for time, but this example wholesale is in the paper. But you can sort of see, if you have a question, what property of water can make a rock break apart? We have a question here about weathering. We have another question here about water. And we sort of are able to, in this cartoon example, put them together. The question, like I showed you in that logarithmic graph, or the issue in that logarithmic graph is that if you're looking for exact copies of the table rows that you want, you're going to get into brittleness very, very quickly and sparsity. You're just not going to be able to do this. So what we do in this paper is we abstract the idea. We say, okay, identical edge, or having explanations with identical edges, identical sentences, is ideal. But what if we abstract that a bit? What if you don't need the same edge? What if you just need to grab something that's from the same table, or from the same table and that connects on the same column, or from the same table that connects on the same column that has the same word in it? So these 3 different levels of abstraction. And because I only have a moment left, what I'm going to say is, it turns out that if you do this, and you do a large Monte Carlo analysis to see if it's even possible to do this, it turns out that by merging, I'll just take this as an example, by merging only 2 pieces of explanations. So you take an explanation 1, you take explanation 2, you break it apart, you put those pieces together. There's enough of natural variation in the corpus that 30% of the time you're going to be able to get the right exact duplicate explanations or explanation sentences. And then most of the rest of the time you're going to get something that's close with varying degrees of closeness. I'm going to call out one specific example to ground this since I know it's very, very abstract. So the question here, Wendy wanted to find out if faster wind speeds increase the amount of wind erosion. What instrument should you use to measure wind speed? The answer is, of course, an anemometer. The gold explanation that we have for this looks like this. Wind speed is a property of weather. An anemometer is used to measure wind speed, and an anemometer is a kind of instrument. This is a very similar explanatory pattern from a different question. And I would like you to think how this could be modified to sort of become this one here, right? Air pressure is a property of the air or the atmosphere. A barometer is used to measure air pressure, and a barometer is a kind of instrument. Looks really similar, right? You can see how you could probably massage this into becoming the gold explanation without too much trouble. This explanation here is at the middle level of abstraction. So this is one better than the worst level of abstraction we have, and it's already really, really close. So this is what I'm working on now. I have a feeling that using these abstracted patterns, abstracted common explanatory patterns, is a way to get this done. I have one more slide, I think, after this, so I'll just go very, very quickly. What are we working on now? We're working on trying to do exactly what I just said, build explanations using a supervised manner. We have a near-term goal, as I said before, of 10,000 explanations in the openly available explanation bank. We have about 2,500 right now. If you want the new ones, just let me know. And I have a feeling that doing question classification is also important in this. We have a question classification system that does pretty okay. The very last bit, and this is the pitch that I'm trying to sell to the reviewers at NSF. You can tell me if it works on you. Little data aggregated is bigger than the biggest data. What do we mean by that? This is a summary. So we mapped out the knowledge to solve 1,700 questions, and we found that only about 4,000 table store rows are required to answer them, right? Using an average of 6 table store rows per question. In contrast, you can go out and mine the web and not do very well at solving this, right? You know, millions of sentences do not answer more than 50% of the corpora. So what's going on here? How can you completely solve the task and explain the answers with only 200%, or with 200 times less data? The answer is, of course, in being able to figure out how to perform this aggregation task. You can combine 4,000 facts into some ridiculously large number of 6-fact explanations, right? Although we have an empirical estimate that a very low number of them, only about 100 trillion, are any good. If you want to know where this number comes from, just ask me. And of course, 100 trillion, which is little data aggregated, is way bigger than any corpus that you're ever going to be able to assemble. Okay, that's it. Thanks for coming.